Hi, I'm Bernardo, and my project this semester is about using automated reasoning techniques to color infinite graphs under a slightly modified notion of graph coloring. Let's start by revisiting the standard notion of a graph coloring. In this notion, two vertices u and v cannot share a common color c if their distance is exactly 1, meaning if they're neighbors. So if a vertex gets color 1, then its neighbor cannot get color 1, it needs to get different color like 2, and then the next vertex can get color 1 again. By repeating this pattern, we have a coloring with two different colors for the infinite path. In the notion that we introduce of distance coloring, two vertices u and v cannot share a common color c if their distance is at most c. So in this case, the vertex with an interrogation sign cannot get color 2, because it would be a distance 2 from another vertex that gets color 2, and that's forbidden by the condition. Instead, it can get color 3. And by repeating this pattern over and over, we get a 3 distance coloring of the infinite path. In other words, the distance coloring number of the infinite path is 3. We just saw that 3 colors are enough. Let us argue that they are also necessary. Color 1 can cover at most one half of the vertices, because in every 2 consecutive vertices, only one of them can get color 1. Color 2, by the same argument, can only color 1 in every 3 vertices. Therefore, their combined density is at most 5/6, which is not enough. By similar manual arguments, one can show that the distance coloring number of the infinite grid with 2 rows is exactly 5. A real challenge, however, arrives when we consider the infinite two-dimensional grid. There doesn't seem to be an easy way to show that there's a distance coloring using a finite number of colors for this graph. As opposed to standard colorings, bounded degree does not guarantee a bounded distance coloring number. It is possible, but hard, to find solutions manually with more than 20 colors. So the challenge we propose is whether we can use automated reasoning techniques to find an optimal solution, meaning a distance coloring of this graph with the minimum number of different colors. How can we use automated reasoning techniques to color infinite graphs? Well, the first step is to transform our problem into a finite one. The case of lower bound is kind of simple. We can just use finite subgraphs. For example, if we want to argue that 4 colors are not enough to color the infinite grid, we can first show that 4 colors are not enough to color this particular 4x4 subgraph of it, which obviously implies that they're not enough for the full graph. The case of upper bounds is more complicated and interesting. Here we need what we call a tiling subgraph, meaning a subgraph for which a distance coloring would imply a distance coloring for the infinite graph by repeating its coloring as a tiling pattern over and over. We can build one of these by adding wraparound edges from leftmost to rightmost vertices and topmost to bottommost vertices. An example that's easy to reason about is the one-dimensional case. Consider the displayed 4 distance coloring of this finite graph. Because of the wraparound edge, we can basically disentangle this into an infinite path with the same distance coloring. The same idea holds for the two-dimensional case. But how can we encode the coloring of these sort of finite graphs in a way that's amenable to automated reasoning techniques? First, let us introduce a naive encoding. Define variables x, u, t to represent that vertex u is getting color t. Then we need the clauses ku that assert that every vertex is getting at least one color. We then need the c clauses to forbid conflicts. These clauses are created for every pair of vertices that are distance at most t, and they enforce that they do not share color t. It's not hard to see that this encoding creates O of m squared k cubed many clauses for an m by m grid with at most k colors. This is too large. And yet, however, it allows us to show some lower and upper bounds for the distance coloring number of the infinite grid. In particular, just by using the naive encoding, we're able to get that this number is between 12 and 15. For the upper bound, consider this 72 by 72 grid that's colored with 15 colors, considering the wraparound edges, and therefore, by repeating this coloring as a tiling pattern over and over, we would get a coloring of the infinite grid. For the case of the lower bound, the encoding for an 11 by 12 grid with 11 colors is unsatisfiable. The Cadical solver is able to determine this in a few hours, even on a personal machine. Let us now discuss a more compact and sophisticated encoding that we call the recursive encoding. We can note that the bottleneck in the naive encoding comes to avoiding conflicts. In particular, when a vertex U gets color T, then no other vertex in the ball that's centered in U and has radius T can get color T. The naive encoding is forbidding vertices in this ball to get color T one by one. This is not efficient. We need a succinct definition of this ball without its center that corresponds exactly to the set of vertices that could not get color T if U gets it. How can we succinctly define a ball without its center? The idea is basically by using smaller full balls that are arranged around the center without touching it. In the case of an odd radius, it's not hard to see that we can do this by using at most 8 different balls. In the case of an even radius, 12 balls are enough. Okay, but how can we describe and logically define these smaller full balls? Well, in order to define them, we introduce variables FUTR that describe that no vertex in the ball that's centered in U and has radius 2 to the r receives color T. Note that because the radius of the ball is 2 to the r, we will only need a logarithmic number of such variables. We can then define these variables recursively by considering that each of these balls of radius 2 to the r can be described as the conjunction of 4 balls of radius 2 to the r minus 1. By putting these things together, we get that the recursive encoding uses O of m squared k log k many variables and the same number of clauses, which is many more clauses than the naive encoding. The main piece of work in progress that we have is to see whether this more efficient encoding, more compact encoding, will allow us to narrow the gap between the lower bound and the upper bound for the distance coloring number of the infinite grid. Let us now, to conclude, present some final results concerning other related problems. We have shown that the infinite grid under Chebyshev distance, meaning that cells are also neighbors of the cells that are diagonal to them. Well, if we consider this infinite graph, this is an 8 regular graph with infinite distance coloring number. We have also been able to show that the 3-dimensional grid under the Manhattan distance is a 6 regular graph with infinite distance coloring number. We have also been able to show that the distance coloring number of the infinite perfect binary tree is exactly 6. Finally, in terms of complexity results, we have shown that computing the distance coloring number of a finite graph is NP-hard, even for k equals 4. But it can be decided in polynomial time whether a graph admits a 3 distance coloring. Thank you.